Hello everyone and welcome to OmicsLogic Genomics Data Analysis Program. I think we should start right now. Okay, you can download the material for today's lecture from the forum site. This is the URL in our educational site. So let's begin with a review with yesterday's lecture. Yesterday, we talked about population genetics and phylogeny. We said how heterogenic different populations are. For example, in this picture, you can see the variants that are found solely in some populations with a darker color in each pie. So, for example, in here, this is a Central European population. You can see that about 10 to 15% of the variants are found only in this particular population and not in other populations. And we said that it is important to study populations independently because, as we have said in the past, the rarer the variant, the more probable it is to cause a disease. The logic behind this is that a common variant won't cause something bad. So studying populations in an international level, we might lose some details because something that is common in Greeks, for example, is not necessarily common in other populations. And then we talked about some initiatives that document variation in different populations. This is in a chronological order. The first for such projects was HubMap, and then there was 1,000 Genomes, which started with the introduction of next generation sequencing technology. And more recently, we have EXAC, which documents variation from 60,000 exomes, and GNOMAD, which is a continuation of EXAC. It has the 60,000 exomes of EXAC, plus some other exomes and genomes as well. And then we talked about phylogenetic trees that are illustration of the evolutionary relationships among a group of organisms. A phylogenetic tree is composed of nodes, the yellow one, and branches, the lines. One branch connects any two adjacent nodes, and nodes represent the taxonomic units. And we have two very similar sequences will be neighbors on the phylogenetic tree and will be connected by a common internal branch. And last, we used the Ebola outbreak in 2014 example in order to construct a phylogenetic tree with the different haplotypes that were identified in Sierra Leone and Liberia. And you can find the example in the demo pipeline in our server site. You can use this URL. And you can explore both the input and output files. Okay, so moving on to today's lecture, we will do an introduction to a very interesting field. We will talk about machine learning. Machine learning has become one of the most important topics in computer science, and it is applicable to any data-driven field. The concept is that a machine learning model can learn from data, and with the generation of new data, this knowledge is continually updated. So machine learning can help us analyze and gain insights from huge data sets. There is supervised machine learning and unsupervised machine learning. In unsupervised machine learning, our data don't have any labels, and we want to group them and interpret them without further knowledge. And in supervised machine learning, we have data that are already labeled, and we use them in order to train a mathematical model, and then this model can be applied to other new unlabeled data in order to gain insights from them. At any time, if you have any questions or if you don't understand something, you can, okay, something is written in the chat. Pratim says that my voice is breaking up. Is this a problem for everyone? Or can you hear me? I don't know what I should do. Okay, great. Maybe Pratim, maybe you should check your connection because I see that, yeah, thank you, Pratim, very much. So at any point, if you have any questions or don't understand anything or you want me to repeat something, you could write on the chat or you could unmute yourself. It is totally fine. Okay, so this is a typical flow of data analysis with machine learning. We first collect data from different sources, and then we use this data in order to describe each sample, each unit in the data. Let me explain what I mean. In our course series, for example, we learned how to analyze genetic data, and we have talked extensively about cancer genomics in particular. So let's say that we have a data set of tumors and some molecular characteristics such as mutation rate or number of mutations or copy number variations, etc. We could use these characteristics in order to describe each tumor, and this would be our features. So from our raw data, we have a unit or a sample, which is the tumor, and this unit, the sample, is described by the features. So we use these features in order to build a mathematical model, and then we can have some results, we can gain some insight. So let's focus a little more on features. We will have hands-on examples later in this lecture. And I hope you will understand everything. So you could say that having a huge number of features in order to describe our data would mean that we could have a great machine learning model. This is not true though. A machine learning model's performance usually will degrade for a large number of features, as we can see in this diagram. So what we usually do in order to be able to not fall in this trap is that we use some methods that help us reduce the dimensionality of the data, because if we have, for example, 200 features for each sample, we could say that we have 200 dimensions that describe its sample. And in many cases, a more accurate mapping in a lower dimensional space makes up for the information that is lost by discarding some variables. So we might as well discard some features. This problem is known as the curse of dimensionality. The idea is that if we select features or if we project our data to less dimensions, excuse me. So feature selection projects an initial set of features from a high dimensional space into a reduced set of features. And still, the data are described in sufficient accuracy. And the common method for feature extraction is principal component analysis that we have talked about in a previous lecture as well. Principal component analysis uses an orthogonal transformation to convert data into a lower dimensional space, and at the same point, it maximizes the variance of the data. The variation reflects the differences between the data, and the resulting features are all uncorrelated, and they are called principal components. So in the statistics lesson, Elia made a great demonstration about the Ebola project, how it showed us how we can separate data based on samples that come from different geographic locations. And this is the result. This is the PCA for the Ebola project. And you can see how samples that come from Liberia, for example, can be separated from samples that come from Sierra Leone. Here, both the yellow and green come from Sierra Leone. But we will do a hands-on example right now about cancer, and we will use some data from Fibrose. Fibrose is the portal that makes available data and analysis from TCGA and the open access data. So Fibrose is, this is the link to Fibrose. I will paste it here in the chat. Okay, this is the first page, and you can see here what data we have. These are different types of cancers, and these are types of data. For our example, I used breast cancer data and lung cancer data. And the reason I use them is because, okay, let me put it here. I think that this is really interesting. You can see that lung cancer is the main region, the main cancer from which both males and females die. And you can see that breast cancer has, okay, it's not common to die from breast cancer if you are a man, and that is because men don't usually develop breast cancer, but it is a big cause of cancer mortality between women. So I chose lung cancer and breast cancer. This is how I downloaded the data. Here you can select the cohort, the type of cancer for which you want to download data. I downloaded breast invasive carcinoma data for breast cancer. And we do genetics, so I downloaded data from mutation analysis. You know, here you can find mRNA methylation, etc. Mutation is a little broader. It has copy number data as well, not only single nucleotide variation data. And if you click aggregate analysis features, you can see a study that has been taken place. And if you click on methods and data and download results, analysis results, you will download the huge compressed file, which if you open, you will find this file. I have put this file in the link that I posted in the forum with our material. These are raw data. I have downloaded with the same manner both breast cancer data and lung cancer data. And okay, here I have opened an Excel. And we can see what our data look like. Okay, this is our data. Here you have the barcode of our sample and some clinical information. For example, data at diagnosis. That, okay, this is breast cancer for everyone, and the stage of the cancer, and some other data. For example, gender and histological type. And here, this is the fun thing. You can find data on mutations. This is what we want to this will be our features. And you can find here, okay, no, this is where it begins. These are mutations in different genes, number of mutations in different genes. And if you go further down, you will find, no, again, this is the same. Let me find it. Okay, here you will find deletions of some loci. For example, here, this is the chromosome 17, the P12 loci of chromosome 17. These are measures of copy number of deletion or amplification. Amplification is right before it. So we have some data of mutations specific for its tumor sample, which is here. And we have this clinical features. So the lung cancer is the same, but it doesn't have the exact same features. So in order to be able to analyze, to make some machine learning analysis for both these type of cancers, what I did was to compare the two files and keep only the features that are the same. Moreover, I discarded the samples that don't have information about the features that I want. So the resulting file is again in the files that I have uploaded in the forum, and the resulting file is, let me open it in Excel as well, is this one. So here we have the ID of the sample, and I have put an ID of my own for next for processing. Here this says that this is lung cancer, and this is breast cancer, and we have the 124, 23 features that are common in both lung cancer. Okay, someone asks what I did to use to create this combined file. No, I used R. I mostly use R. And someone else asks if it's possible to share my workflow to keep common features amongst two different cancer types. Okay, yes, I will note it and I will share it. Well, this is not, I will share it of course, but what I did is I created two data frames, one for lung cancer and one for breast cancer. And what I did is to compare the names of the features. So I only kept the common ones, that's all. And then in order to be able to use the server side, I put the samples in the columns and the features in the rows. This is what I did. Okay, so you can see here, this is mutations in PIK3CA, mutations in P10, RB1. These are all mostly cancer-related genes, and this is why they are in both the data sets. This is the rate of non-synonymous mutations. That means the number of non-synonymous mutations divided by the total number of mutations. And this is the rate of synonymous mutations. Okay, so here I have changed something I don't understand. It's A to something mutations, A to T, A to C. I'm sorry, I have changed something and it has two dots here and I don't understand what exactly it is, but it's a mutation from A to another nucleotide, amplifications in some uh, loci, deletions, and copy numbers of big loci in the chromosome. And these are the common features. And you can see here that there is great difference between its different type of features. So here we have number of mutations. We have 0, 5, 6, 4, etc. Here we have a 8, and we have a number which is very, very small. In deletions and amplifications, we have even some measures of deletion or amplification. So we have a great variance as well. And in order to be able to use this data, I normalize the data. This can be really easily done with Excel as well. And there are many different ways of normalizing the data, but this is what I use. This performs a rescale between 0 and 1. So all the data will be between 0 and 1. And I did this for each category of data. So I performed this first for the mutation number, for the rate, and for the amplification. So this is the concept. So before the normalization, I had this, and after the normalization, you can see that all my numbers, all my features are between 0 and 1. 0 will be the feature with the minimum value, and 1 will be the feature with the maximum value. Okay. So after doing all these things, I continued performing PCA. You can find this in the URL here, but let's do this together as well. Okay. So someone asks do you have, I don't share my screen. Is that right? Yeah, that's right. Okay, so someone asks if I normalized all the features. I normalized all the features indeed, but I performed a normalization for each category separately because there is a lot of variance. And if you have small numbers against big numbers, I don't know what would happen. So I performed each normalization for each category separately. Okay, so let's perform a PCA. We will use the utilities in order to perform the PCA here. And okay, let me show you the file that we will use. Of course, I didn't do all these things in the big file. This is the normalized file. Okay, and you can see that it has 900 samples. So we can do this in 900 samples, but I didn't do it in 900 samples. I have made some smaller files. So for PCA, we will use this one. It's a file with 24 samples. Okay, give me a moment. Okay, now it's okay. So we have all the features that we had before, and we have only 24 samples. And I have separated in 4 categories. These are lung cancer other, This is lung squamous cell carcinoma, so this is a different histological type of this one. These were the more frequent ones, so I used them separately, and the other ones are different types of cancer, of lung cancer. This is breast cancer infiltrating ductal carcinoma, a type of cancer that begins in the ductal cells, and this is breast cancer, other type of cancer. So I used this file for PCA in order to be able to reduce the dimensions of my data. So by clicking Add Files, I will use this one, Cancer Types Normalized. Continue. Start. And then I will perform quantity normalization in order to transform the data in a way that they will have the same distribution. And let's transform our data to logarithm. And then PCA. We will not use any filter. We will use the standard parameters. And we will click on it. Okay, PCA cancer, for example, and then run pipeline. All these pipelines run very quickly, but I have opened the pipeline as well here. This is the pipeline from the URL that you have in the presentation. And here I have the output. I will open it first on a notepad. Okay. This table shows the principal components for each of the samples. Which pipeline did I start? I started the utilities. Okay, let me go again. I click on utilities. File upload. Okay, I uploaded the file. Yeah. So start, quantity normalization, and PCA. That's all. So in this, in the result file, you will see that we have 1, 2, 3, 4, 5 principal components, and it says here that the first one is responsible for 31% of the variation, and the second one is responsible for 24% of the variation. If we open it in Excel, no, I have already done it in Excel. So I will open it in Excel. It's the exact same file, but I have inserted a scatter plot, and then I have selected the data, and if I make it a little bit, you can see that we could say that breast cancer is somewhere here. Of course, breast cancer other and lung cancer other are different types of breast and lung cancer as well. So considering that we have these two parameters, we could say that we have a separation. Gray and yellow are breast cancer types as well, so they seem to be separated by from blue and orange, which are lung cancer. And of course, we can use the principal components as features as well. Is someone talking? No. Okay, so are we okay with it? Should I move on? Yeah, this is the result. Okay, if you don't have anything, we should move on. Okay, apart from PCA, a method that is used often is linear discriminant analysis, or LDA. This is a supervised method, which means that I remind you that we have an input of labeled set for training, not like in PCA that we didn't have any labels. Well, in our example, we had it, but the algorithm didn't use it. So the idea of LDA is simple. Given the training sample set, LDA tries to project the sample into a straight line so that the projection points of samples of the same class are as close as possible, and the projection points of the samples of different classes are as far as possible. So here, if we try to project in one dimension, these are two-dimensional, we try to project in one dimension, this is a bad projection, and here we have a good projection, which separates the classes very well. So unlike PCA, which tries to maintain data information as much as possible, linear discriminant analysis, its purpose is to make the data points more distinguishable after dimension reduction. So we don't want to find the principal components that have the more variance. We want to find how to separate the data. Okay, and let's perform a linear discriminant analysis. You can find again the demo pipeline here in the slides, but let's do this together as well. Okay. We will click on supervised analysis. Okay, first let me show you the data. We have again breast cancer and lung cancer data, and this is the trained data set. Okay, we have again the same thing as before, the normalized features, and these are our samples. We have 40 samples, and these are the classes: lung cancer, other, lung cell carcinoma, breast cancer, other, and infiltrating ductal carcinoma. And the test data set is this one. I have only put 2 from lung cancer other because in our original file we had less samples, and 3 from lung squamous cell carcinoma, 3 from infiltrating ductal carcinoma, and 2 from breast cancer other. So we will use the trained data set in order to train our LDA algorithm, our LDA model, and then we will use the test data set in order to classify this data. I have put a class here, but the algorithm doesn't take them into account because they are in the test data set. So this file could be as well without this row. But we know the classes, we only do this for demonstration, it doesn't affect anything. Okay, so as we said, let me go again in the beginning, we will click in the data mining section in the supervised analysis. These are all algorithms for supervised analysis, and we will upload both the train and the test data. Okay. And then we have to select our groups. This is the train will be used in order to train the model, and this is the test will be used in order to test the model. and we will click on continue. Start. Okay. LDA. Here it says what LDA does. And you can see that we can use the output of LDA in order to train another machine learning algorithm, but we won't see it today in today's lecture. Today we will click on it and we will see how the data are separated. Let's put the name in the pipeline, LDA stands for classes. And run pipeline, it will run, but we have already run it. No, this is not it. No, excuse me, I might have, this is it, so I might have closed it. Okay, you can download the outputs from here. The old results that .zip will have all the results, and the RPath will have function in R that run this particular pipeline. So let me go in my already downloaded output files. Okay. So this file is the discriminant function. It tells us the scaling values which tell which variables are more significant. So roughly speaking, the absolute value of these particular values will tell us which variables were the most important for its linear discriminant during the analysis. And this way we can select the most significant ones. I forgot to tell you that now that we have 4 classes, we will have 3 discriminants. So n minus 1 discriminants. So our projection will become in n minus 1 dimensions. In our example, we have 4 classes, so it will become in 3 dimensions. So this is the result of the discriminant functions. How well each feature has performed in each dimension. And here we have the plot. The plot, let's open the other screen. This is the plot. This is not very easy to interpret because it is a 3-dimensional plot that it has been visualized in 2 dimensions. But you can see here, for example, if we take into account discriminant 2 and discriminant 1, you can see here that the breast cancer other has clustered together. And no, this is breast cancer, but I mean IDC and infiltrating ductal carcinoma has clustered together as well. So we can see that there is a separation. This is the statistics. The statistics take into account both the train and the test data sets. We see that we have achieved an accuracy of 0.95. If we had a bigger training set, this could be even greater. And you can see here that this is the true. This is called confusion matrix or truth table. These are the true identities, classes of each sample, and these are the predicted. So you see here that we have 12 breast cancers that were truly infiltrating ductal carcinoma, and where all of them were classified as infiltrating ductal carcinoma. But here we have 8 breast cancer of other histological type. 7 of them have been classified as the true class. but one of them has been classified as infiltrating ductal carcinoma. And the same it's with lung cancer, but this is a little bit expected because, as I said, there are not many samples from the other types. So, yeah. And what else does LDA give? Okay, it gives the prediction for the test samples. We should go here in order to see. Is this it? Yeah. So we would have other three squamous, three IDC, and two breast cancer others. So let's go again here. No, okay, this is not in the same order, so I can't really tell. But we have 1, 2, 3, 4, 5, 6, 7 that have been classified as breast cancer, which is not correct because we had 3 breast cancer. IDC. This is I have changed the name of the class before I show you the so I'm sorry for the confusion. But in the trained dataset, we have a better accuracy. You can see here the one that has been misclassified from the other lung cancers and the one from the other breast cancers. And you can see that all squamous cell carcinomas and infiltrating ductal carcinomas have been classified correctly. Okay, do you have any questions before we move on for the last part? You can unmute yourself as well.
I have a quick question. This is Ian Townley.
Yeah, thank you.
So for the discrimination function, the numbers there, I might have missed it. What are you looking for just in the numbers? I understand how the grouping works, but are those numbers, when it gives you like negative 1.9 or positive 2.4, what is that?
Okay, so the absolute value of these numbers tells you which variables were the most important, which separate the data of different classes better. So it doesn't matter if it's negative or positive number. We take the absolute value, and the higher the absolute value is, the best separation it provides.
Oh, okay. That makes sense.
Okay, thank you. Do you have any other questions?
I have one more question.
Oh, okay.
Yeah.
Go ahead.
Yeah, the accuracy was 0.95. Would you consider that a good value? Is that something that you could work with, or would you try to get it larger?
No, I think I would try to train in a different way my data in order to achieve more accuracy. So yeah, this is an example. We only use how many? 40 samples. We have 900 samples for the training data set. We could use more, and maybe we could see which of the features are the best in order to to utilize only these features and not every feature that we have. But we just show here how it is done and what is the concept, the basic idea.
Okay, thank you.
Thank you very much. Do you have any other questions? I think someone else had something to ask.
Right. So it's basically a continuation of the answer which actually already gave. That being that, to begin with, you took all the features, but then after PCA and LDA, you found out that there are, few features which contribute the most. Mm-hmm. And, that would mean that if you make a second iteration of this whole pipeline, then, during that time, you just take the, more, let's say, contributing features and see how the accuracy kind of, gets better, if at all. So, so that would mean that we have to again, repeat this process. This is one thing. Is there any way, maybe in the pipeline, where, it becomes more in an automated fashion, where, based on top, I don't know, 50, 100, whatever, based on the parameters which we select, it runs like two pipelines. First pipeline, which would tell that which features are more contributing, and the next pipeline where only the more important features are taken. So this was one of the questions, or maybe a suggestion, or just a question. Second point is that, do we also get sensitivity and specificity, kind of parameters in this output, so that we know, like, what's going on, rather than just the accuracy?
Okay, these are very nice questions. Okay, so the first one, I think it's more or less answered, because here we saw how we can distinguish the more important feature. So this is a first part of the analysis, but this is where the today's lecture is focused. So this is the answer. Yeah, I would use the more important features in order to perform a more detailed analysis. So for the second part, you ask if the sensitivity and the specificity are calculated. Unfortunately, in the files, in the output files, it is not provided, but from the confusion matrix, you can calculate it. So I don't remember, I'm sorry, I don't remember exactly the formulas. I always confuse them, but
Okay, no problem.
if you just Google it, you will see, okay, so sensitivity is true positives divided by positives in general. So
Okay.
you can use the confusion matrix and calculate it very easily. Is that okay?
Okay, sounds good.
Okay. So let's move, if you don't have anything else to ask, let's move to the last section of today's lecture. Is that okay? I guess so. And for the last section, we will see what is factor analysis and how it is performed. So factor analysis is an analysis of correlations between factors and patterns in the data. For example, in a multi-factor experiment, we could expect each factor to have an effect on a different subset of data, and additional factor combinations have their own unique influence. In our example, we have an experiment where both type of cancer and another factor which could be gender of patient can play a particular role. So the type of cancer and the gender are different factors, because we could have different mutations in women with breast cancer and different mutations in men with breast cancer, and the same applies to the lung cancer as well. So in order to understand what role each factor has, we have to perform factor analysis. And we will see another pipeline for factor analysis. First, let me show you the data that we will use. This is the file. FM stands for female male. Okay. I don't know why at first it gives this error and then it's okay. So again, I have made this file. I have selected data from females with lung cancer and males with lung cancer. So here we have lung cancer, M for male is F for females. And here we have breast cancer again. These data are for females and these data are for males. And we have all our features. So we will go in our server side and we will go here, factor analysis. We don't upload, in this pipeline, we don't upload data in the beginning, but after the analysis, the setting of the tools. So if we click on factor analysis, it says here what exactly factor analysis is and how many factors we want to take into account. If we click add, we want to add two different factors, A and B, which have two classes each. So we have two types of cancer, lung cancer and breast cancer, and we have two genders. And now we will upload the file. We said it's DFM file, female, male. Okay, so we will click on check. We have many samples, so we will add them here in this particular box. So we have breast cancer and males who will go in A2B2. Breast cancer and females will go to A2B1. So we have B factor is for different genders, okay? And lung cancer and males will go to A1B2. And lung cancer and females will go to A1B1. So all the males are in B2, all the females are in B1, all the lung cancer are in A1, and all the breast cancers are in A2. And we will click on end. Okay, factor analysis, cancer, sentence. Yeah, I won't run it right now because we have already here the pipeline that I have run in 2 days ago, which is, okay, this is the pipeline. And if you click on download pipeline out file, you will see one file, which is this one. And let me open it in Excel. Sorry for this. So we have all our samples, and the features, for example, have been transformed with the factor analysis pipeline. And here at the end, we have some test statistics that show how each feature contributes to its factor, or each factor contributes to its feature. So if we click filter them, you will see here, here we have A1 and A2. This is the test statistic between A1 and A2. A1 and A2, I remind you, is for the cancer type. So if we figure it from largest to from smallest to largest, this is a p-value. We usually keep the p-values below 0.05. And we will see that here, these 23 features that have a p-value lower than 0.05 are the ones that are the more important for a factor, for a cancer type factor. And these are the features that are the more important. The same if we sort from smallest to largest for the gender factor. We can go here and we will see that now we have 15 features that are the most important for gender factor. And these are these features. And here, this is the most interesting because if we combine the two factors together, we can do a statistic test and see which features are the most important for the combination of the two factors, which can separate the features best based on both the cancer, not the features, the samples based on both the cancer type and the gender of the patient. And if we sort from smallest to largest, you can see that we have 18 features that separate best for both the factors. Okay, someone asked to explain again what the numbers mean. You mean here in the F statistic, these are p-values which indicate if there is a significant difference between the two the samples in each factor. So here we have A1 and A2. A1 is for lung cancer and A2 is for breast cancer. So the factor analysis has performed an F test which says for which features there is a significant difference between lung cancer and breast cancer. And if we keep p-values that are below 0.05, which is the p-value that we usually keep, we can see that these features are the most important. Yeah, this is p-value. This is for gender and this is for both factors combined. Does factor analysis pipeline generate any visualization figure? No, unfortunately, it doesn't generate, but I don't know if it should. I think it is mostly in order to pick the features that you want to use, depending on what the question is that you want to ask. Thank you. So this was today. If you have any questions about anything that we have discussed, feel free to ask them now.
All right, so I have a question. So prior to factor analysis, what we did, we took, let's say the data, and in that the data had values both from, let's say, males as well as females. And based on that, we performed PCA, then LDA. But in factor analysis, what we did, we further segregated our data into, let's say, several different quote unquote subclasses where the data would be treated as kind of, separate, modules, one module coming from males and another one coming from females. So is that how we are kind of trying to go kind of little deeper into analysis so that, by layering on top of our analysis, let's say factors, we would be able to make even better predictions or more quote unquote accurate predictions?
That's exactly what it is. And we got a little bit deeper. And if you see the raw data,
understood.
For example, from breast cancer, you have many factors that you could take into account. For example, you have here the population, which could play a role in germline variation, and you have other clinical data, and you could use any of them in order to perform a particular analysis. Yeah, this is it.
But the first analysis, for example, LD or PCA, was done on like all the factors taken together, right?
Yes. Yes.
Okay.
Exactly.
Okay. So I still have one little question related to that. Now, we try to normalize some of the sub-factors or subclasses earlier, as you explained, like, you normalized number of variants, then you normalized deletions or amplification values separately. And then you also said that, all these values still are not normalized when you compare, let's say, the values for number of mutations to values which come by deletions or amplifications. So in spite of that, we were able to plug those values into PCA, and PCA was able to figure out that even though there is kind of great difference between different classes, nonetheless, there are some factors which would be, let's say, the most important as compared to, or rather, some of the features which are more important than the other. So where is this kind of integration of data taking place? Because, quote unquote, these data are coming from many different classes. So how PCA or LDA is able to take care of that, or how it is able to do some kind of internal normalization to generate an output which is kind of, as straightforward as what we saw.
I don't know if it makes an internal normalization. I think that if we normalize the data per category, of course there are other ways to normalize the data as well, but I use the simpler one, which is pretty okay. So if we normalize the data per category, they all, in our example, they all came between 0 and 1. So I don't think there is, they are quite normalized, I believe. So, yeah, for example, in PCA, we perform quantity normalization after our initial normalization in order to put our data to make them have the same distribution. So this is another type of normalization as well.
Okay.
Yeah, they are between 0 and 1, so they are pretty normalized.
Okay, okay, I got it. Okay, and then the pipelines were also able to handle categorical data, right?
Yeah.
Okay, all right.
Just wanted to follow up on that question. So I understand, like, the normalizing the data made all the different types of data kind of equal, because they're just between 0 and 1 based on their range or scale and variability. Would you ever weight different factors? Have you ever done that in your sort of analysis to say, okay, I know like this sort of factor carries more weight phenotypically than another sort of factor? Does that make sense?
Could you please explain a little more, because I didn't catch what you want to say. I'm sorry.
Yeah, my question is just, so I understand for this analysis, for like the PCA, the data you took, it's all this different types of data, and we normalized it all to be in a scale of 0 to 1.
Mm-hmm.
And that gives equal weight to all the different types of factors that we're looking at.
Mm-hmm.
Would you ever weight those factors? Say, okay, this is on a scale of 0 to 1, but this one, we're not only going to allow it to go up to 0.8 or something like that, as a way to distinguish, like, I know this sort of data tends to carry more phenotypic weight if we're talking about a disease,
Okay, so you mean about the features, is that right?
The features, yeah. Would you ever weight them?
Okay.
Other than just...
these are all ways to weight them. When we say that we have some features that are more important than others, these are ways we want to see how the classes are best separated from some features. So maybe the TP53 mutation rate is a great feature which separates excellently the classes. So these are ways to identify which features are most important and which features help us understand how the classes are separated. And this has nothing to do with normalization, but the reason we have to normalize is to eliminate errors from noise.
Okay, thank you.
Thank you.